In the special case of linear systems, full state feedback, we provided a solution, but all others, say dynamic feedback for linear systems can come from LQG, which we didn't discuss in detail. But nonlinear systems are always much more difficult, and we didn't offer any solutions. And in a way, feedback dissipative systems actually will provide that kind of solution, at least for the class of dissipative systems. And in short, basically, if you have two dissipative systems in feedback, you will have stability, right? And then we will see, obviously that's not a very general, I mean, it's not specific in terms of the conditions under which this is true. We will look at the conditions, and basically this part of the lecture is essentially going to be talking about this key result, right? So we are going to assume that we have, for the lack of better terminology, let's call it a plant. The plant, that's the one we have in front and that needs to be controlled. And we assume that this plant is dissipative with respect to some supply rate, and also assume that there is a storage function that's positive definite. And now the question is, we'll assume another system, a nonlinear system could be, which is also dissipative with respect to its own supply rate and its own storage function. And typically this part could be actually something that we design, therefore it's completely up to us in terms of how we can design. So therefore this R sub C, for example, the supply rate and storage function could be picked on our own. It could be linear, it could be nonlinear, anything. So the standard result state in the form of negative feedback interconnection, but actually it does not matter. It's just a matter of convention. There is some sacred nature to negative feedback in say the standard control or tracking and things like that. But here we don't have any such thing. These are two dissipative systems that are connected. In fact, this result could easily be generalized to even more complicated interconnections involving more number of dissipative systems. Anyway, for the time being, we are going to assume there is a negative feedback between these two connections. What does that mean? As the picture essentially shows, the output of the first system, the plant, is going to be connected to the input of the controller. I'm going to call the second one as controller. And the output of the controller, which we denote using Y sub C, is going to be the input of the plant with sign reversed. So U equals minus Y sub C and UC equals Y. So that's what we mean by negative feedback interconnection. And of course, when we do this feedback, essentially we will have a closed loop system. It will have hopefully a zero equilibrium point, and then hopefully we can conclude that this particular system is going to be Lyapunov stable. And in fact, the answer is the result is quite straightforward. If R and R sub C are such that R plus R sub C is less than or equal to 0 with this specific negative feedback interconnection, right? I mean, in reality, you have to look at it as R of U comma Y plus R sub C of Y comma minus U is less than or equal to 0 for all U and Y. Then the zero solution is of this negative feedback interconnection is Lyapunov stable. And we will look at some specific examples to understand this, what we mean by this, right? So if in addition, basically we can have a stronger assumption that each of these two systems are exponentially dissipative as opposed to simply dissipative, then we can guarantee global asymptotic stability. And these are the two kind of extremes. We can have some conditions where it's slightly weaker on one of the systems, but we can have certain assumptions such as zero state observability and things like that. So there are many different ways of proving these results, or some form of such a result where we have bare minimum Lyapunov stability, asymptotic stability in some cases, and some cases exponential stability, right? So that's in a nutshell the primary result, and it's fairly straightforward. So what it says is, if you have a plant and you want to design a controller, if the plant happens to be dissipative with respect to supply rate R with the negative feedback interconnection, ensure that the controller supply rate is such that R plus R sub C is less than or equal to 0, and then we are done. Of course, both of them have to have positive definite storage functions and things like that. To see better insights and better control over in terms of how to design these feedback systems, let us actually consider the special case of quadratic supply rates. Things become quite simple there, right? So I'm going to now talk about the quadratic supply rate case where G is dissipative with respect to this QSR supply rate, and of course the corresponding controller also is assumed to be dissipative with respect to a quadratic supply rate, its own quadratic supply rate. And I apologize for missing Q sub C, S sub C, R sub C there. Again, both of them have positive definite storage functions, and again we'll assume the standard negative feedback interconnection like we did earlier. So here instead of we assuming R and R sub C, the summation is less than equal to 0, we introduce one more scale. No big deal. We could embed that R sigma into R sub C, or sometimes you have systems that already you have two systems that are dissipative with respect to R and R sub C, and if you can somehow figure out a scale that still gives you this R plus R sigma R sub C is less than is equal to 0, then can show that the closed loop system is Lyapunov stable or asymptotic stable as the condition may be. So, but then this R plus sigma R sub C simplifies to basically checking this particular Q hat matrix, which is combination of your supply rate matrices. Again, I want to repeat that basically this Q and S and R and the second supply rate has to be with subscript Q sub C, S sub C and R sub C, and this Q hat matrix has to be negative semi-definite, and then that ensures Lyapunov stability. Like I said, if this Q hat is assumed to be strictly less than 0, then we can probably say something more, or on the other hand we have exponential dissipativity and things like that, and we can conclude also asymptotic stability, right? So this again is a special case of the previous result, except it's in a form that's a little bit more palatable. You can actually work with matrices and things like that. Otherwise there's nothing so intricate about it, right? So therefore now we'll get into feedback interconnection of passive systems or special cases of dissipativity. In fact, you can almost say basically this was the original result, so to speak, and then basically what we have in terms of Willems proving the general dissipativity and feedback interconnections is much newer in terms of generalization of what we have in front of us. So the result is very simple. If G and G sub C are passive, then basically the 0 of the negative feedback interconnection is indeed Lyapunov stable and respectively asymptotic stable if you assume exponential passivity. So let's actually try to understand. We are now no longer abstract in terms of R plus R sub C and things like that. We have very specific supply rate here. So what I'm saying is the plant is passive, which means V dot is less than or equal to 2 times Y, and the controller is also passive with respect to its own supply rate, but its own supply rate and its inputs, right? But of course the negative feedback interconnection tells me that basically U sub C is Y, the output of the plant is input of the controller, and the input of the plant is the output of the controller with a negative sign. So when I substitute that, essentially I'm going to get V sub C is going to be less than or equal to minus 2Y times U. So if I add these two, V dot plus V sub C dot is less than or equal to 0, implying Lyapunov stability if all the other conditions like the closed loop feedback interconnection has a 0 equilibrium, and of course we assumed anyway positive definiteness of each of the storage functions, right? So it's as simple as that. So it's nice to know that if you have two passive systems, then we'll have Lyapunov stability, right? If on the other hand, if we have something like one of them is passive, the other one is input strict passive, input output strict passive, then and then zero state observability will guarantee that the closed loop system is asymptotically stable, right? So what we're saying is basically V dot is less than or equal to 2 uy, right? And V sub c dot is input output strict passive, so that means 2 minus 2 uy, right? That's after putting the negative feedback interconnection, and minus epsilon 1 u transpose u. This is actually y sub c transpose output strict passivity with respect to the controller, and then the input strict passivity, which becomes output of the, I should put transpose everywhere. Anyway, so this is essentially what we have. The plant is passive, and then the controller is input output strict passive, and then basically by replacing u with y sub c and u with minus y sub c and y sub and y with minus u sub c and things like that, we will get this equation. So summing all that, we will get v plus vc, both derivatives, is going to be less than or equal to minus epsilon u transpose u minus epsilon transpose this thing. And so well, I mean, I could leave this as y sub c here, okay, and then this of course is less than or equal to 0. And what does this mean? So this, if you recall our LaSalle theorem, essentially we have to consider v dot is equal to 0 the case, in which case basically on the limit set y sub c is equal to 0 and y is equal to 0, right? So I don't know if this argument needs to be expanded. Basically, if you recall, if we have some Lyapunov function v tilde dot less than or equal to 0, then x of t goes to the largest invariant set, right, which is a subset of the set v dot of x is equal to 0 or some subset of that, right? But v dot is equal to 0 implies that y of y sub c is 0 and y equals 0. So on that invariant set, these two are true, and therefore what do we know? These are 0 state observable. So basically, if y sub c is 0, its corresponding input is also 0. So u sub c is 0, and of course u is 0. So each of the systems have output 0 and then input is 0. So that simply means x sub c and x is going to be 0, right? So that essentially shows asymptotic stability. This is a cool argument of LaSalle for these dissipative systems. And what we essentially showed is, if one of the systems is passive, the other one is input output strict passive, 0 state observability gives us feedback interconnection to be asymptotically stable, right? Of course, we can also conclude that if both are input strict passive, then the same logic goes. You can conclude it yourself. It's a very similar and straightforward. And of course, you can imagine if both are output strict passive, the same thing can be said, right? So either one of them is passive, the other one is input output strict passive, or either both of them are input strict passive or both of them are output strict passive, then 0 state observability of both the systems guarantee asymptotic stability, right? So the last one is the most interesting. It actually does not belong to feedback interconnection of passive systems, but non-expansive systems. I just put it at this instead of isolating that one single bullet to a different slide. So if you have G and G sub c to be non-expansive, such that the corresponding gains gamma and gamma sub c is less than 1, then the 0 of the NFI is Lyapunov stable, right? So let's look at that particular result. So what are we saying? Basically, v dot is less than or equal to gamma square u transpose u minus y transpose y, right? And v sub c dot, this is the non-expansive of the plant, and then the same thing is true with its own input and its output, right? But that's equal to gamma sub c square y transpose y minus u transpose u, right? And then I'm going to now sum this with some scale. I don't know what I'm doing, but basically since I have this option of scaling it, I'm going to add the scale. And I can show that this composite Lyapunov function, we can call it for the closed loop system, where sigma is of course positive in all the cases where I have sigma. What I'll get is basically gamma square minus sigma u transpose u plus sigma gamma c square minus 1 y transpose y, right? And I'm going to pick let sigma to be such that well, you know, I'll show you a simple case. Let sigma to be exactly equal to gamma square, right? That's not going to work, but well, let me do one thing. Let me do this thing. Let sigma is equal to some gamma square plus epsilon, right? So then let's see, and then basically therefore sigma gamma square minus 1 is going to be gamma square plus epsilon times gamma c square minus 1, which is gamma square gamma c square minus 1 plus epsilon gamma c square, right? So so basically what we'll end up with is basically v dot plus sigma v c is less than or equal to you know, I'll get minus epsilon u transpose u, right? And here I'm going to get plus gamma square gamma c square minus 1 plus epsilon gamma c square times y transpose y, right? Now if gamma times gamma sub c is less than 1, so there is some gap between these two. So the epsilon should be small enough, this entire thing, you know, this is a negative number, right? This is a negative number. This should be small enough positive number, so epsilon could be picked very small. So we can ensure that so there exists epsilon such that gamma square gamma sub c square minus 1 plus epsilon gamma c square is still negative, right? That's what we're trying to do. So essentially what we are going to get is v plus sigma v, the derivative, is less than or equal to minus epsilon u transpose u minus some other epsilon c, which is essentially the basically this entire thing, which is a positive quantity, and we get that, right? And of course we can replace this with y sub c and then use the same logic as before and then conclude asymptotic stability, right? So essentially what we have are quite interesting results here, in the sense that if you have two passive systems feedback, we have Lyapunov stability. If we have any of the them to be input output strict passive, then we end up with asymptotic stability. If both of them have input strict passivity and things like that, we will have asymptotic stability, right? But if you recall all of these things, if some system is passive, then we know it's Lyapunov stable. If it is input output strict passive with zero state observability, then it is asymptotic stable with the input being 0 and so on. So you have all these nice properties for this each of the systems with its input being 0, but when you actually put them in feedback, luckily they don't go wild, and then that's what is nice about this. And then the last result, if you notice, is basically the generalization of the so-called small gain theorem, which was like a bounded real for bounded real systems in feedback. It's basically generalization of that to nonlinear systems, right? So it's good to know that basically such results, these are very special cases and classical cases, but in general we can therefore use similar techniques to basically essentially design a controller which is somehow connected to the plant in a certain way, r plus r sub c is less than or equal to 0 with the negative feedback interconnection, and then we can prove stability, right? What does it mean in terms of anything else. I mean, on one hand, we can actually use this as a general technique for designing controllers. And let me remind you, basically, once we have a dissipativity of the plant, we'll have, obviously infinite number of plants that satisfy this particular condition. Not everything, but you have an entire class of dissipative systems and feedback that can actually stabilize the closed loop. What does that mean? Basically, we have ability to pick the most optimal, and then optimization is something that comes later in the course, perhaps a couple of lectures later. And that's nice to have that optimization problem. But more than basically having a class of controllers and optimize, that's a very important aspect. We can actually apply and then show many of the results that we have seen before are special cases of this particular thing. And then earlier we have seen this result for linear systems. I'm going to show it for nonlinear systems. We didn't really get to the details of that in a nonlinear system. So if I consider a nonlinear uncertain system is of the form x dot equals f plus g times delta times h, right? This is basically very similar to x dot equals a plus b delta c x. You can rewrite this as a feedback interconnection of some system and a static feedback system, right? In the previous case, basically we could have the G sub C part could be dynamic or static and things like that. Okay, we'll get to that in a second in terms of what it means for the storage functions and things like that. Okay, so then the result actually quite straightforward. If we know that somehow the plant is dissipative, it allows a bunch of uncertainties that will keep the closed loop system stable. And basically here it's a positive feedback interconnection, so you don't see any minus anywhere. But what you notice is the supply rate of the feedback system. Okay, I'll go back and then perhaps show you detail in my handwritten stuff. But this one is well. Let me show you perhaps. Okay, so what we have is some G with output Y and input U, and then we have positive feedback interconnection with respect to some uncertain system, which is we call as delta, but it is a static system. So if I'm going to call this as U sub C and Y sub C is output, of course y equals U sub C and U equals Y sub C. There's no negative sign anymore. What we want is basically, if you recall, Q hat is some matrix that involves some Q plus R sub C. There was a minus there and things like that, and then S plus S sub C transpose S plus S sub C plus S transpose, and then R plus Q sub C. We had something like that, and then we had to show basically if this is true, then we get so, and that's why we kind of reverse that, right? And we can basically show the system is going to be stable. Right? The zero solution of the nonlinear uncertain asymptotically stable for all these things. Now, there are a couple of things that we should need to do. We need to pay attention to. I assumed exponential dissipativity. The second thing is basically the static system. The storage function happens to be, you can pick it to be 0. So, therefore, the storage function of the plant becomes the Lyapunov function of the overall system, and then that's okay because there is no specific state corresponding to the static system. Right. So, in a way, a static system is like a nonlinear system with empty state, the state of 0 dimension, so to speak. So, we use that trick to basically show that this is indeed true. So, the same trick therefore can be extended to absolute stability, and then it's a matter of imagining basically instead of having a delta matrix multiplying the input of that particular block, which is going to be Y in this particular case, output of the plant part of it, and the same result goes through. If G is exponentially dissipative, and then Y transpose QY plus Y transpose SU plus U transpose RU, that's the supply rate, then basically the zero solution is going to be asymptotically stable for all nonlinearities that belong to this particular sector, right? We know this terminology of sector, essentially satisfying that inequality. Again, this Q comes here, whereas S comes in the middle, and the transpose R comes here, and of course the overall sign is reversed, so that the summation that Q had that we're talking about becomes identically 0, right? So we'll have V dot less than or equal to 0, right? And then V is exponentially dissipative, so V dot is actually less than or equal to minus epsilon V of x plus the 0 part, the both supply rates adding to 0, right? So this is what we were doing earlier, and then that's why I confidently said that basically if you understand dissipative theory in a generic fashion and understand how feedback interconnections of dissipative systems work, robust stability of any kind, most of the results that are out there, except the complex, very complicated frequency domain ones, even those when you actually start trying to go into time domain, they become special cases of dissipativity. In fact, it's a matter of sitting and actually do a bookkeeping, but there is I don't think there is any result in robust stability that cannot be proven using dissipative theory, right? Maybe slight generalization of dissipative theory is actually more than enough to understand robust stability and of course absolute stability, right? So I mean, this is end of basically week 8 lectures, where we have seen dissipative systems are quite interesting. They're generalizations of standard systems where the basic systems in analysis we didn't have input and output. Here we have input and output, but they satisfy very specific properties. That supply rate has to be greater than or equal to 0 if the initial condition is 0. That implies there is a storage function. But the nice thing about it is if you actually take feedback interconnections of such systems, we get stability for free, right? So, this is kind of the theoretical aspect of controls so far. What we'll be doing over the next several lectures and the rest of the lectures, so to speak, we'll talk about bits and pieces of various topics. And I'm planning to show basically application of some of the theory we learned to classes of systems, because applying all the things that we have done so far to provide a general computational method for designing controllers is not something that's easy, right? Except some special classes. So we will be looking at special classes, and we will look at general theory for certain problems, but we will also look at specific examples of problems where we can actually have an idea how to solve a particular problem. So the first topic in that category of controls that we're going to look at is stable adaptive control, right? Thank you.